Hello! You may remember that I built a giant Rubik's Cube for EMF Camp 2022. If not, don't worry, here it is. It was a lot of fun to build, it was a nightmare to transport, and it only ever ran for one weekend nearly 4 years ago, and it's just been in storage ever since then. Unfortunately, it rained on the EMF weekend in 2022, which was the one thing I really hoped didn't happen, because I ran out of time to treat the plywood paddle switch mechanisms to prevent the water soaking into them. They all swelled up and most of them seized completely or wouldn't return to the center properly. This left the cube unplayable at the end of the weekend. Also, each facelet was just one big pixel. So, what if, for EMF Camp 2026, I made version 2 with some of these LED panels. These would give me 48 by 48 pixels per facelet. I could do some fun shader effects on these. This project is going to take some effort to pull off. There's a few hurdles in the way. Firstly, I don't have enough of these panels. This is the only one I have right now. I need 45 of them. I know a guy who has 15 more of them that I think he's keen to donate to the cause, but that still only gets me a third of the way there. I had a look at how much it might cost to buy enough of these panels brand new. The answer is somewhere in the range of £5,000 to £8,000. Patreon, YouTube memberships. Oh, excuse me. If I had that kind of money to spend on this project, then I would. Unfortunately, I don't. So I'm probably going to have to get a lot of donated panels or a lot of donations to an LED panel fund. Links in the description. Oh, wow, I've got a really bad cough today. The extra tricky part is that these panels need to be physically compatible so that I can mount them all together on the frame of the cube, and also visually compatible. These pixels are square and have a diffuse lens on the front. That appears not to be that common, actually. So if I mix and match these with other panels, there will be obvious differences and it might look terrible. In the worst case, it might mean that the cube is not playable because the red, orange and yellow colours are not sufficiently recognisable across the different panels. The next challenge is fixing the paddle switches. I need to remake them all, and ideally make them out of plastic this time. That shouldn't be too hard. I have the design files for all the parts that need laser cutting for that, and I have access to a laser cutter. I can reuse most of the electronics from the version 1 cube, but I do need some additional hardware to support the LED panels. I've got most of that already though. Another challenge is that I need to find a way to mount all of these panels together in a cube shape. The timber frame from the original cube is quite flimsy, and these LED panels are very heavy. I'm going to have to make something more robust, but hopefully I can reuse the existing edge sections that the paddles mount on, since those are still in good condition and they are very robust. Lastly, and this is the fun part of the challenge, I need to rework the software. That's the easy place to start, and it should be fun, so that's where I'm going to start with part 1 of this video series. Right here, you're watching that right now, congrats. There's a lot of things I need to think about, so let's get into the details. First of all, let's look at what software I already have. There's 3 parts of the software stack. At the lowest level is the software that interacts with the physical world. To read the paddle switches, I used a Raspberry Pi Pico. This is a little microcontroller board with a reasonable amount of I/O pins, so I don't need to do anything too fancy to read all the paddle switch inputs. This is what I call the device software. On version 1 of the cube, this Pico also connected to the string of LEDs that were used to illuminate the facelets. It could control all of these LEDs from a single GPIO pin because these LED boards each use a WS2811 chip to form a chain of LEDs. Each one passes data onto the next, and you can quickly stream the data into the first LED and trust it to pass the rest down the chain. The device software has sufficient logic in it to know when the cube has been solved. This might seem like something that should happen at a higher level, but I deliberately chose to do it here because this is the device that actually controls the LEDs. So it knows for sure if the cube appears to the player as if it is solved, even if the device's model of the cube gets out of sync with the model used by any other layer of the software. This means you'll never end up with someone thinking they completed the cube, but the timer doesn't stop and they don't get congratulated. The next layer of software is what I call the service program. And this is designed to run under Linux and provides the network interface required for the remote display to show the state of the cube and to initiate the game and the timer. The service program is what connects to the device, the Raspberry Pi Pico, to tell it how to scramble and to find out what twists are being applied and when the cube is solved. Finally, the highest layer is the control software. This is the graphical user interface for the cube, and it's what connects to the service layer over a network. So, what needs to change for version 2? I can't use the Pico device to control these big LED panels. The bandwidth needed to drive this many LEDs is beyond what's possible with a Pico. Or at least, even if it is possible, I'd rather do it from a more capable computer so that I can have fancy shaders on the cube. These LED screens normally accept input from HDMI or DVI connections, so I intend to have a fairly standard desktop PC with a modest graphics card in it. This is going to generate the graphical output for the LED panels. I will still need the device software though, since it is the part that reads the switches. I will simply not use the LED output from the device layer. The easiest way to make this happen is to add this as a feature of the service program. This means I also want the service layer to become responsible for deciding if the cube is solved. Since it's now the part that is generating the visual output, it is the part that holds a model of the cube that can't be inconsistent with what the user sees. So, to summarize, I need to add graphics output to the service layer, disable the solve detection in the device layer and add it to the service layer, and write some cool shaders. The LED panels can be formed into an arbitrary shape with the driver software. I have a virtual display of a fixed size, and I can map each square of LED panel to a particular square on this virtual display. I will map the 45 panels into a 5x9 rectangle in the top left corner of the virtual display. I will then have the service program open a full-screen OpenGL window, and then only use the top left corner of it, making sure to have my 45 squares sized correctly so that each one lands in the right place on the cube. I've been working on this already, and I have this to show for it. It looks very small because each facelet is only 48 by 48 pixels. Let me zoom in for you. Once this is actually rendering for real and using the entire screen, it will look like this. Just the top left corner being used. I can visualize what this will look like by mapping this video capture onto a cube in some 3D rendering software. Currently there's no smooth animation of each twist, it just jumps from one state to the next. Even on the old version of the cube, with 1 pixel per facelet, there was some animation. So in part 2, I'll show you how I add animation to this video output. If you want to be notified when part 2 arrives, subscribe to me here on YouTube. Don't forget to gently pat the like button an odd number of times, and if you want to financially contribute to this project, I've got a lot of LED panels to obtain, that'd be very much appreciated. You can join the Patreon, or the YouTube membership, or just send me a one-off super thanks on YouTube. See you in the next one.